So I will go ahead and introduce Dr. Bruce Maggs, our keynote speaker. Bruce has received 3 degrees in computer science from the Massachusetts Institute of Technology. And I love that he lists the first 2 as SB and SM, which is a hint to where they came from. His advisor was Charles Lyserson there. And after spending a year as a postdoc at MIT, he worked as a research scientist at the NEC Research Institute in Princeton. And then he moved to the computer science department at Carnegie Mellon and rose to the rank of full professor. And then, most relevant for our purposes, he was on he took a 2-year leave of absence from CMU to become a founding employee of Akamai Technologies. And he served as its first vice president for research and development. In 2009, he joined Duke University, where he is the Pelham Wilder Professor of Computer Science. And in 2013, he was part of a team that received the inaugural SIGCOMM Networking Systems Award for the Akamai CDN. And he was also named an ACM Fellow. He's currently on leave from Duke, but we still have arguments, he and I, about basketball because we have a friendly rivalry there between Kentucky and Duke. For those of you from other parts of the world, there's a strong Duke-Kentucky rivalry in basketball. But he's currently serving as Director of Engineering for Emerald Innovations, which is developing technology for health sensing and analytics, which is something different. But he graciously agreed to give this keynote and talk about the economics of content delivery. So Bruce, thank you very much. And I'm going to turn it over to you now.
Thank you, Ken. So I wanted to first say thank you for inviting me to speak. It's really an honor. I'm so sad that we can't all be together. In fact, the only reason I accepted the invitation is I thought that I would come to Montreal and hang out with you all and we would have a lot of fun. Nevertheless, Tomas and Ken, thank you for inviting me. As Ken said, I recently retired from Akamai after 21 years of service. I'm doing a new thing, but I think I'm still qualified to talk about the economics of content delivery. I've also timed my talk, and I don't think it's going to go long. So I encourage you to go ahead and ask questions in Slack, and Ken could interrupt and pose them to me if you'd like. I'm pretty unflappable, so I'm not worried that I'm going to be distracted by any questions. Thank you. So the talk will be on the economics of content delivery. And I hope this is interesting to an audience that is interested in information-centric networking, because in the end, I think for any technical solution to fly, the economics have to line up behind it. I think you could argue that the combination of Google and Akamai is sort of a crude information-centric system, although it's one that is done kind of at the application layer without networking support. And so it's kind of interesting to think about, well, if you were going to do this right, how would you do it? Although, we don't necessarily want to put Akamai out of business, at least not until I'm well into my retirement. So I want to start with a little bit of the history of the commercial content delivery business. And by that, I really mean the rise of independent content delivery networks or content delivery services. In the beginning, Akamai kind of boldly just started deploying thousands of servers around the world at hundreds of locations, and then went to content providers and said, hey, why don't you let us take on some of the work that you're doing to deliver your websites right now. In particular, just give us the images that appear on your web pages and let us deliver those. And our argument was that, that's 70% of the bytes. So if you hand those to us, we can speed up your page load times because our servers will be closer to the end users than yours. And we'll try to make sure they're never congested. And furthermore, you'll have a reduction in the amount of infrastructure that you need to buy and manage. We'll give you sort of scalability on demand and your job will just be focusing on the content and less on your infrastructure. So there's these two value propositions here: reducing the latency for page load times and reducing the investment in infrastructure, allowing content providers to buy it on demand. Let's look at these two things. Here's a chart showing the impact of page load time on conversion rates for e-commerce websites. I like the term conversion. A user is converted, which is sort of like has religious connotations, if they buy something, which, yeah, so that makes sense. And so you want to convert every user, but it turns out that studies have shown that if you slow down the delivery of the web page, your conversion rate goes way down. And here it's sort of showing that, yeah, it kind of depends on the platform, because users have different expectations on different platforms. But, you know, past 3 seconds to display the web page, the conversion rate really takes a hit. And while this is a report from Akamai, which, as you can imagine, would be expected to demonstrate a really big effect, you can find similar studies that have been done by Amazon and Microsoft and Google, and they're in different contexts, but they all show that even fractions of a second can have a pretty big impact on conversion rate or number of searches that somebody does or amount of time they spend on a website. So reducing latency has big value to e-commerce websites. Now, on the infrastructure side, there are a number of content providers who have these periodic, let's say, events where there's suddenly tremendous demand for their content. And then after a short time, it's over. And a good example is the gaming industry, where there are periodically new releases of software, and there's tremendous demand. For example, back in 2018, the company that makes the game Fortnite released a new season. And in gaming terms, in Fortnite terms, a season means a new version of the game. And suddenly, Akamai faced a peak of 37 terabits per second to download this software. Similar things happen when new versions of iOS come out, or Mac OS or Windows. There are these moments when there's just peak demand that's gigantic, but it doesn't really make sense for Fortnite to invest in enough infrastructure to handle this demand like 4 times a year and then let that infrastructure sit idle. It makes more sense for them to be able to just scale on demand and, you know, hand this off to a content delivery network. There are similar phenomenon with video events. For example, the World Cup soccer match, or in the old days, whenever Steve Jobs would give a talk to the Apple faithful, there would be these very short-term, massive spikes in demand, and it was convenient for the content providers to be able to just sort of rent that capacity and not have to invest in it. Let me show you an example of how this original service of handing off the delivery of images to the content delivery network was done mechanically. So here's a dummy web page I created called xyz.com, and here's the HTML for the home page. This would be served from the web server www.xyz.com that's operated by xyz.com. And in this initial version of the web page, they're also serving the images. I've put them in orange here. So one of them is a logo and one is a background. And they're both served by the same web server that serves the home page. Now, if Akamai convinced this content provider to let them serve the images, then the change might be as simple as just changing the domain name here in the document itself, and then changing the DNS configuration so that the authoritative resolution of the name ak.xyz.com was delegated in some way to Akamai rather than to xyz.com. And so when the client's browser read this document in, noticed that there were some embedded images with new names that have to be resolved, that resolution would ultimately be performed by Akamai, who would return the IP addresses of a web server or web cache somewhere that would have the image, and the browser would go there to get it. Now, this is the very earliest service, and interestingly, this service was crafted with a lot of help from the webmaster at CNN, who explained to Akamai sort of, these are the kinds of changes that I'd be comfortable making to my website. And they had to be things that could be very easily undone. So for example, this could be undone just by reverting the changes to DNS configuration. Of course, Akamai's hope is that once the content provider starts using the service heavily and reduces their investment in infrastructure, they can't really ever undo it. But that's an economics lesson. Economics lesson number one, make your customer dependent on you. So things have really changed. And I'm going to talk about 2 or 3 fundamental shifts in the way website delivery occurs today. But one really interesting shift is the move to full site delivery by content delivery networks. And what I mean by full site delivery is that every byte sent by a client upstream to a website must first pass through an edge server belonging to a content delivery network. And similarly, every byte sent downstream from an origin server belonging to the content provider passes through an Akamai edge server on its way to the client. This is quite common. About 20% of the websites in the Alexa top 500 list now use Akamai for full site delivery. And we're going to talk about why they do this. It's a little bit embarrassing. You're going to see throughout this talk examples of where arguably horrible things are done because, you know what, there's just no network support for doing this right. And so we put on a lot of band-aids. But this particular mechanism is motivated in part by a kludgy thing called the split TCP optimization. And here's how it works. When a client establishes a new TCP or TLS connection, the time it takes to establish that connection before any useful work gets done is determined by the number of round trips that must be performed, which is maybe fixed or maybe not, depending on what can be cached, times the latency for each round trip. And if the client is trying to connect to an origin server that's far away, the latency for each round trip will be large, and so the time to set up the connection before anything useful gets done will be large. The split TCP optimization says, let's have the client connect to an edge server, which can terminate the TLS connection. And the edge server is hopefully close to the client, so the round trip latency is small, and there's a quick, immediate connection setup. Meanwhile, the edge server maintains a permanent, persistent connection back to the origin server that's already ready, and so there are no long round trip times needed for the client to send its first data up to the origin server and for the response to come back. In this picture, I've shown that, and I've also shown that, well, once you put this edge server as the first hop, you can also start to do fancy things like include an alternative overlay path through another server belonging to the CDN back to the origin server in case maybe the default route provided by the internet, the one that the persistent connection used, isn't so good. So maybe you set up more than one persistent connection, another one through an overlay server. Now, in addition to this split TCP optimization, which is one of the primary motivations for this, Bing was an early user. I don't know that they do that anymore, but this was just to reduce the time it took for users to connect to the search website. Second motivation is to protect the website from various kinds of attacks. We'll talk about that function of a CDN later in the talk. But the edge server can do various things like filter out obviously bad requests and also provide capacity, to be able to, in general, serve anything that can be cached at a very large amount of capacity. One kind of scary implication of this is that if the edge server is going to terminate the TLS connection, it has to both operate DNS for the primary domain like worldwideweb.bankofamerica.com so that it can direct the clients to the edge servers. And in addition to that, it has to hold the private keys so that it can succeed in the TLS setup. And that means that basically the content provider has given full trust to the content delivery network, because the client or the client's browser cannot tell that it's really talking to Akamai as opposed to the content provider. The Akamai has the credentials, and so if an insider at Akamai chose to, or if Akamai was compromised, there would be a sort of potential here for a person in the middle attack that couldn't be detected. Well, that makes you a little nervous, but that's just the way it is. By the way, you know, there are other ways that a content delivery network could direct clients to its servers, other ways besides DNS. And Akamai in some cases does that, and we'll talk about that later. But the primary mechanism is DNS, right? So this is the Akamai kludge to deal with the fact that, hey, there's no network support for just asking for some piece of content and having the network go and fetch it for you. As you know, that's not the current IP model. This service has grown tremendously since it was first introduced in 1998. I probably could get rid of any kind of images that were produced by Akamai's marketing department, so I'm no longer obligated to use them. This one has always bothered me because it looks like thermonuclear war, but it's supposed to show, I don't know what it's supposed to show, maybe where users of Akamai services are located. Today, there are over 240,000 servers in the network. Primarily, these servers are sitting on other companies' networks. It's only recently in the last few years has Akamai built its own backbone. But for the most part, you should view the CDN as a virtual network that relies on other companies to provide hosting and network connectivity. And so the servers are on 1,700 different networks, meaning 1,700 different ISPs around the world, at 3,300 physical locations in 750 cities across 130 companies. Ken, I saw a chat or something. Do you have a question for me?
Actually, that was from me, I think. Just telling you, I'm turning on my video so you have some feedback instead of a blank wall there.
Oh, thank you. Please pretend to laugh at my jokes.
I will always laugh at your jokes. Thanks.
Okay, thank you. Okay, great. So that's kind of a scale of the physical infrastructure. Now, on the customer side, the services are used by all of the largest e-commerce websites, all the top 20 worldwide, the top 30 media and entertainment companies worldwide, 16 of the 20 largest banks worldwide, and all the major antivirus software vendors who use Akamai to deliver updates to their software and to their virus lists and so on. Here are some daily statistics. They actually may be a little bit old because historically in the last 22 years, pretty much almost every year, the amount of traffic and the peak numbers that Akamai delivers have roughly doubled. So it's been this crazy exponential growth. But the last time I collected these numbers, a daily peak was typically around 80 terabits per second. Akamai would see requests from over 600 million distinct IPv4 addresses every day. And I think at this point, even more distinct IPv6 addresses every day. That may surprise you, but the reason is that the carriers, the cellular carriers, are using IPv6 on the mobile devices, and they're making native IPv6 requests to Akamai. Akamai serves over 3 trillion HTTP requests per day. That's a big number. If you divide by the number of people in the world, I think that comes out to several hundred per person per day. And Akamai collects over 260 terabytes of compressed logs every day, like log of every HTTP request that it's receiving. I started with a discussion of delivering static images, but you know, in terms of bytes, that's not where the action is today. We're going to go into other Akamai services, but let's step back to economics again for a minute. So this is a picture of the Akamai Network Operations Center. By the way, I'm giving this talk from Cambridge, Massachusetts right now. As Ken said, I'm on leave from Duke. I originally came up here to visit MIT, but I got sucked into a startup company. However, I did rent an apartment 1 block away from Akamai, and that glass building there is Akamai's brand new headquarters. And what we can see in this picture is Akamai's Network Operations Center. And when I teach classes on distributed systems, I always ask my students, what do you think this room is for? And they raise their hand and say, well, it's a place where you can monitor what's going on in the system. That's true. And if anything goes wrong, you can try to fix it. And that is false, okay? That is not what this room is for. This room is to impress investors and potential customers, all right? If you had a system this big and it required humans to tinker with it to keep it running, no hope. It would be all over. And so I think if you look closely, first of all, I think these people are actors, because I know when this photo was taken, and I don't recognize any of them from the NOC. I've given many tours, and I've never seen any of these people before. But even more importantly, if you look at their screens, they're all viewing CNN.com, all right? So this is economics lesson number, well, I don't know, we're on our economics lessons. You got to look good, but your system should, you know, operate itself as much as possible. Here's another economics lesson. So where does the money come from? You may know this already, but I think it's good anyway to be explicit about it. I'm going to present this sort of from the perspective of the content delivery network. Where does the money come from? It comes from one source. It comes from the content providers. They're paying to have their content delivered. They want it done reliably. They want scale. They want low latency. They want accountability. But the end users are not in this picture from the content delivery network's perspective, at least in terms of flow of money. The end users pay some money to different parties, but they don't pay directly to the content delivery network. The content delivery network is a business-to-business type of operation. The primary costs for delivering the content are paid by the content delivery network to 3 types of parties. They pay the internet service providers or networks or carriers, whatever you want to call them, for bandwidth. They pay the co-location providers and the IXPs for rack space and energy and interconnect. And then they pay the hardware vendors for the servers themselves. At least today, Akamai owns its own servers. I think there's a foreseeable future where Akamai maybe rents virtual machines from carriers or other parties, but for now, Akamai buys the servers and has them installed. If we look at cost of goods sold, and so these are costs directly related to delivering content. They don't include engineering costs or real estate costs or travel costs, but they just include costs of delivering the content. It breaks down roughly as follows. And by the way, I'm not giving you insider information. I was told that I could share these numbers by a current Akamai employee, and they're a little bit rough, and they actually vary a lot geographically. Like the breakdown's different in Europe than it is in the United States, but these are good enough for ballpark figures. Akamai pays about 25% in bandwidth. Okay, cost of goods sold, 25% of the cost is bandwidth. And where Akamai pays for bandwidth, it pays according to the industry standard 95/5 rule. And the rule is basically this. You take a month's worth of usage, which basically means bits in plus bits out at a particular switch port, and you sort it according to 5-minute intervals. So for every 5-minute interval, you compute the megabits per second average for that 5-minute interval, And then you go to the 95th percentile for the month, so nearly peak but not quite peak, and you take a reading there. And maybe that comes out to 1.3 gigabits per second. And then you pay for some rate that you've agreed on. Like, okay, I'm going to pay you $2 per gigabit per second. And I'm making up those numbers. I don't know what they are, but that's all negotiable. Bandwidth is a major cost. Next, we have co-location. So this is how much you pay to the organization that is physically hosting your service. And we'll do a more detailed server, physically hosting your server. And we'll do a more detailed breakdown of that next. And then 25% for server depreciation. Now, at the moment today in 2020, server depreciation is calculated over 4 years. That's kind of the typical lifetime of a server in the field. Until recently, it was 3 years, but as improvements in server technology have slowed down, the servers are now living in the field longer. It was interesting that in the past, as the traffic on Akamai's network was doubling every year, the number of servers was only going up by 40% per year. And that's because the servers themselves and the network capacity where we installed them and in their interfaces was going up even faster. Which is probably still roughly true, but you know, it slowed down. There's 25% other. I'm not really sure what to say goes in that category. Who knows? But if we go and look at the co-location breakdown, the cost is about 40% for rack space, 40% for energy. And it used to be, like 10 years ago, that when you rented a rack, you had to pay for the maximum amount of power that was available at that rack, like 1,200 watts, whether you used it or not. And that wasn't a very good system because, first of all, we ended up paying for energy we weren't using, but also, and this is a little insidious, it took away any incentive to reduce the amount of energy we were using. Now, almost everywhere, our energy use is metered. We only pay for what we use, and now there's incentive to try to save energy. For example, you know, the best way to save energy is to turn off a server if you're not using it. That, by the way, though, is a tricky thing because if you're trying to keep your caches kind of up to date and kind of have each server know what's going on in the system and be available on short demand in case there's a spike in demand, well, turning off a server is a bit of a risky thing to do. And I don't know how often we really turn off a server, but you might try to reduce its power consumption partially. Then there's 20% other. And so you sometimes have to pay for interconnect within a facility. Like Akamai says, I want my switch to interconnect with this particular network that I'm going to peer with in the facility, and we have to pay the host for that. Or sometimes you host servers in one building because that's where there's rack space, but you want to peer with a router belonging to some network in the building next door or down the street, and you have to pay for interconnect between buildings. So there's other costs. So I want to get a little technical now, and this may be interesting to adherents of ICN, because I'm going to talk about how it is that Akamai directs clients to the servers that have the content they want. And we'll also get into the economics of this. But first of all, as you all know very well, the current model, service model of the internet is not, oh, here's the content I want, please provide it. Or here's the service I want, please provide it. That's a beautiful model. That's kind of the ICN model. But the IP model is, hey, here's a packet, deliver it to the destination address, right? And so everything else has to be built on top of that. And when Akamai receives a request from a client for content, it has to figure out, okay, where are we going to direct that request? And first of all, we do this before we see the details of what the content is. It's based on the DNS name, so we really only see who the content provider is. And we don't really keep track of where every object is currently cached. Why did I even say really? We don't keep track of that at all right? So the decision about which server cluster we want to direct, by the way, I should stop saying we, I should say they or Akamai or CDNs in general, but the decision is made mostly on the basis of which server do we think would give the best performance if it had the content? And let's hope it does, because we don't want to cache miss, but that could happen. Second, well, okay, do we have capacity at that server? And third, and by the way, these are in not necessarily the actual order, where's it going to be cheapest to serve from? So what we'd really like to do is serve from places where we don't pay for bandwidth and we don't pay for co-location. And it turns out that there are many no-brainers where this is actually true. Akamai has invested a tremendous amount of effort into its partners program, where it has convinced universities, large companies, small ISPs and ISPs in foreign countries that they should allow Akamai to install servers in their networks for free. And the deal is that the Akamai offers to provide service only to their users, like, only to the university community, not outsiders, giving them better performance, and also reducing the amount of traffic on the network link that the organization has to its network service provider, because less content will have to be brought in from outside. But in exchange, Akamai would like to have free bandwidth, free energy, and some notion of physical security for its servers. When this can be done, it's easy. If I'm at Duke, then my request gets sent to some servers that are on a network called the North Carolina Research and Education Network. And Duke is directly connected to that, and so is the University of North Carolina. That is the top 2 basketball schools in the country. Okay, see, we got a reaction out of Ken. Ken, I might have to mute you here. Otherwise, though, when there isn't a no-brainer, we have to serve the content from servers that are hosted in some data center where we pay for bandwidth. And so how is that done? Well, Akamai, you guys know, the current network protocols don't really try to optimize for performance. If you look at a protocol like BGP, it doesn't really even have any notion of performance. You might think that, AS path length translates to performance, but that's delusional, okay? So the only way we can know whether or not we'll get good performance from some Akamai cluster to some end user is to do active measurements around the clock. And here's how it's done. Every night, we collect the logs from our DNS servers, and we find the network addresses of all the resolving DNS servers that sent queries to Akamai the previous day. We sort them. We take like the top 500,000 of those. And then for each of those, from about a dozen different Akamai clusters, we do a trace route. And after we've done all of these trace routes, we look at them and we figure out where they intersect. So in this example, the numbers 1, 2, 3, and 4 represent resolving name servers. And we've done trace routes to each of them from a bunch of locations. And what we discovered is that the paths from Akamai's clusters to these name servers all intersect at some point X, which we call a core point. And that's a router which we can view as sort of straddling the core of the network and the edge of the network. So the name servers are in the edge somewhere, and X is their gateway to the core. We call X.
Can I interrupt and ask a question? There's a question in the Slack channel about whether is it actually traceroute, or do you use some other tool because of traceroute is not always totally accurate when you have things like MPLS and stuff going on in the middle of the network.
I think it's really traceroute. You're right. If we have MPLS going on in the middle of the network, traceroute isn't going to show us what's going on under the covers. But we really care mostly for what happens at the very edge. Like we want to see this exit point from the core into some access network. And I don't think MPLS interferes with that too much. However, I readily acknowledge that this is a very imperfect process, and we're doing it without cooperation from the network providers. Of course, we've got a long list of do not ping and do not trace route network addresses if you ever get a complaint. But hey, I told you there was going to be ugly stuff that had to be done because we don't have network support. And this certainly falls into that category. But it's really trace route, okay? So, and by the way, this is a simplified picture because there are all sorts of new wrinkles like, once Google and OpenDNS started introducing sort of DNS for the public, just set your name server to 8.8.8.8, that kind of wreaked havoc with this system. And then new things were added so that the resolving name server could provide the /24 prefix of the client who made the request. And Akamai will process that information too, okay? But just bear with me at a high level.
Sorry, there was actually a little discussion about that in the Slack channel too, about that very thing.
Yeah. So if you decide that you want to let Google know about every website you're visiting, in addition to everything you search for, fear not. Akamai cooperates with Google and OpenDNS and a few other very large DNS operators, and will accept the /24 client prefix, and we'll work on that. When it first came out, anybody who switched to 8.8.8.8 would just see abysmal performance because we would have to say, well, let's hope they're near that name server. But no, that's a special case that's taken care of. It's not a huge percentage today, but it's something to keep in mind, right? We're still mostly seeing requests coming from the resolving name servers provided by ISPs and universities and so on, but that could change over time. There's also an implicit assumption, I think you guys may know it, which is that we're kind of assuming that clients are close to their name servers in the network. That's a very strong assumption that Akamai makes. It's not always true. It's probably bad for you to set your name server manually to be in Tokyo if you're in the US, because Akamai is going to serve your content from Tokyo if you do that. Maybe you want to do that, but it's not good for performance. So wait, I've still got to continue, okay? We identify the set of core points, and it's new every night. Well, maybe it doesn't change that much, but they're recalculated every night. And then throughout the day, for each of these core points, there's continuous pinging, like several times per minute, from each of maybe 10 to 20 Akamai clusters. And we record the latency and the packet loss. And we provide a score, which is a combination of those two. And we're trying to understand for each core point, which Akamai cluster can get to it with the lowest latency and the lowest packet loss. And that would be a good cluster to serve all the clients that are using the name servers behind this core point. Okay, so you can see this is very, very different from what many ICN proposals try to do, where you say, this is the content I want, and then there's smart routing directly to the content. Okay, first of all, we're not doing it at that level. We're making the decision based on which cluster we think has the best performance. We hope that we have a high cache hit rate so that the content that's requested is already there. And so the focus is really on performance and not on performance sort of with blinders to whether the content is really there. Okay, so these 500,000 name servers get reduced to about 30,000 core points. Of these, about 7,000 account for 95% of end user load. And we ping these core points continuously. I think probably pinging all 30,000. I don't know. These numbers also fluctuate over time. But this is an interesting number, the 30,000, because it kind of tells you the true granularity of the internet. Like how many different parts are there out there, right? 30,000. You got to cover them all. Let's talk about bandwidth and how much we pay for and how much we don't. So you've now seen there are sort of two categories. The no-brainers where we we've got the servers in the organization that hosts the users directly, and we can serve them for free. That's about 40% of our bandwidth. Then we've got all the other users that we have to serve out of servers that are in data centers where we're paying for bandwidth according to the 95/5 rule. That's about 40%. And then we also have about 20% of bandwidth that we're typically paying for, maybe sometimes paying for, sometimes not paying for, that goes from our edge servers back to our origin servers, or sometimes we actually have a cache hierarchy. So edge servers may contact a parent in the cache hierarchy, or they may pass data through an overlay intermediate node back to an origin server. But this is sort of, and by the way, these are rough numbers, not secret numbers. These were again given to me by somebody at Akamai that said I could mention them. Okay, so we talked about static content, but really most of the bytes are in video. And so soon after Akamai was founded, soon after it launched its static content service, it had to get into the video business. And back in 1999, video delivery was a little different. So it was delivered from proprietary servers, and the main proprietary formats were Real, Windows Media, QuickTime, and Flash. And then there was proprietary players, which was software, despicable software that you had to install on your machine, and it would take over your machine and force you to watch a lot of crazy advertisements and stuff like that. And video was delivered over UDP, and bandwidth was less plentiful. So there was an effort to put a lot of smarts into the client and the server to try to optimize the delivery of the video. And Akamai first got into streaming when Steve Jobs asked Akamai, partially in exchange for a 4% investment in Akamai, to build a live streaming network that could carry his speeches to the Apple faithful. And notice here that there's a major distinction between video on demand or canned pre-recorded video and live video. Live video like last night, a live video like today where anything could happen, where Ken could start shouting over me if I went off the trails here. So I'm going to talk a little bit about that live video network. One of the things in this economics talk, though, is I'm going to tell you about things that have been phased out because the economics changed or the technology changed, and also some things that failed completely. Well, or yeah, that's fair to say. So this is what the original live streaming architecture looked like. There was some video that was encoded, and the encoded video was passed to an Akamai server called an entry point, which fanned it out to Akamai servers called reflectors, which then passed it on to clusters of edge servers that were running the proprietary video format servers, the Real servers or the Windows Media servers or whatever. And then these servers delivered the video in a one-to-one fashion to end users. And the goal of the delivery network, everything from the encoding to the clusters of edge servers, was to get a clean copy of the stream into each cluster that needed it. And this network was agnostic about video format. It just thought its job was to deliver clean streams of UDP packets. Didn't care if it was Real or Windows Media or whatever. So the interesting thing, I guess, about this network was it had a mechanism that allowed for redundant delivery. So if there was a cluster that had a user or maybe multiple users that wanted a stream, and it wasn't able to get a clean copy from just one reflector, it was allowed to pull redundant copies from other reflectors. And the hope was that by pulling redundant copies, it would be possible to get at least one good copy of every packet and reproduce a clean stream to send to the end user. And this network was dumb. So it didn't even do any error-corrected code. It didn't use error-correcting codes. It just strictly used redundancy. And one of the reasons for that is it didn't want to introduce any latency. Now, you can do better than this, for sure. Most of the ways you can do better in terms of reducing bandwidth involve some buffering and error correcting, but not all necessarily. But one of the reasons for not reducing latency is that a major application for this network was carrying quarterly financial calls from publicly traded companies. And it was very important to the SEC that the people who called on the phone were not getting information earlier than people who listened on the internet. So there was sort of stringent delay requirements. You couldn't just put a lot of buffering into this. As I said before, this was all UDP based. Guess what? It's gone. And it's too bad because I hold a patent on this. But you know, video delivery has changed. So today, everything is delivered over TCP and HTTP. And in fact, the servers are just dumb web servers. They're no longer proprietary web servers. They don't even know they're delivering video. They just know that they're receiving requests for some byte range in some pretty big file. Now, for a live video, it's a little more complicated, but not much more complicated. The server itself doesn't know what's going on. It just thinks I'm getting requests for data. All the smarts are now in the client, and largely the sort of special purpose client software has gone away. It's all being done in the browser. Not entirely, right? Right now I'm running a Zoom client outside of my browser, but nevertheless, Zoom is video conferencing though. That's a little bit different than watching a movie. The client is running JavaScript. It's making all the decisions. And the kind of decisions it makes primarily are, hey, am I getting this data at the current encoding rate without interruption? Or should I switch to a lower encoding rate so I don't need to pull as much data? All right, and that client is making that decision, and it conveys that decision to the server just by changing the URL. The server otherwise doesn't know, it's, oh, okay, someone asked me for a different URL. And the server doesn't know what that is. It's really frustrating. In fact, when I look at the Akamai logs, the clients these days don't always even, clients and web pages, they don't even label stuff with MIME types. So it's very hard sometimes to tell what type of object the server just delivered. I mean, not only does the server not know, but looking in the logs, I can't tell either. The best thing I can do is say, oh, well, actually, by the way, I don't have access to the logs anymore. In case anyone from Akamai hears this, don't worry. But you can look at who the customer was, and maybe there's a customer code in there, but that says this is our video, but who knows? Now, things have gotten even more complicated with the introduction of a new party in the content delivery business called brokers. And these are companies like Conviva that had this diabolical idea of going to the content providers and saying, hey, we're going to let you shop around and use multiple CDNs. And we're going to give you client-side JavaScript code that will pick from among multiple CDNs to help you lower your costs. And what this code does, call me jaded, but since I spent many years at a high-end and expensive CDN, is it goes down a list of CDNs in order of cheapest price first until it hits one that gives acceptable performance. That I don't blame them. Okay, that was a good idea. But so brokers now introduce the second level of decision that's happening at the clients. As I said before, the vast majority of bytes served by the CDN are video. However, video delivery is a highly commoditized business with low profit margins. And part of the reason is the brokers, but you know what? It was that way even before the brokers. And the reason is that it's not that hard to set up a video delivery service. Video is not latency sensitive. So if you put servers in a dozen or a couple dozen well-located data centers, right off the bat, you can do a pretty good job delivering video, right? You don't have to make some massive investment in a worldwide deployment. And so it's easy to go into the business of video delivery. What are the high margin services? Well, I've mentioned some of them before. One is low latency content delivery. It's high margin for two reasons. One, it translates to profits directly. And two, it's not easy to do. There's no alternative but to move the content close to the end users. And even little tricks that reduce latency often can be sold at high margins. The other thing that's not so well appreciated is that with 20 years of experience of integrating websites onto the CDN platform, the CDN has learned about 1,000 different little bells and whistles that the content providers would like to have applied to their content when it's delivered. Little stuff, nothing interesting maybe from an engineering point of view, but little hooks that you can sell separately as value-added items. For example, content provider wants to show several different versions of their web page and see which one leads to more sales. You flip a switch and the CDN server does A/B testing. That's just one example, but there are 1,000 of those. The good thing about this from the CDN's perspective also is that the CDN wants to turn on as many of these as possible, which will make it extremely difficult to pull the page off and switch to some other CDN, right? So video delivery, that's commoditized. Homepage delivery is not commoditized. Really tricky to move from one CDN to another. And finally, a growing business for CDN is protection from denial of service attacks and other types of attacks. Nobody wants to pay for protection when they're not being attacked, okay? Protection's a racket, right? We'll kind of make sure nothing bad happens. But when you're under attack, you're usually willing to pay a premium for protection. So let's talk about this new part of the content delivery business, which is the shielding the content providers. Akamai has two architectures. One is built into the web content delivery system I've told you about already. And the other one is a more generic packet filtering system. So DDoS attacks are just simple volumetric attacks where the attacker tries to overwhelm the site with requests. And they often look for amplification, where this attack somehow requires only a small and easy to generate request to create a large or difficult to generate response. These attacks are growing year by year, like crazy. Like in 2018, there was an attack at almost 1.4 terabits per second against GitHub. And it was using a vulnerability in memcached, open memcached servers around the internet. Notice that while this is big and certainly could crush any individual site, 1 terabyte compared to Akamai's daily peak of 80 terabytes isn't so big in terms of overall capacity. The website protection system, it just, in normal operation, clients make requests, they get served at the local edge server, or maybe they're passed on to the origin server, or maybe they go through some relay. But if attackers show up and try to bring down this system, yeah, they could bring down individual servers or clusters. It's hard to protect an individual component, but then we can just send users off to other places. And the TTLs on our DNS are very short. They're under 1 minute. So we can move users around pretty quickly if we have to. And any attacker who has enough capacity to, say, bring down half of Akamai's network already has enough capacity to bring down the whole internet. And so at that point, maybe they have bigger fish to fry. These servers can do more than just provide capacity. They can filter out obvious attacks like SQL injection attacks. They can also record malicious or login attempts, like just repeated failures to log in, and they can throttle clients that fail to log in too many times. And it's amazing how many tens of millions or hundreds of millions of failed login attempts Akamai sees every day. The other network for protection of services uses a different mechanism, and it's not DNS. Akamai has established a few, maybe a dozen or more, maybe 20 packet scrubbing centers around the world. And to protect a service like a game server, we ask the operator to advertise with their DNS resolution to advertise with an anycast address that's been established at each of these packet filtering centers. And when attackers try to send their traffic to the origin server, hopefully we can identify it and mitigate it at these packet scrubbing centers while allowing legitimate requests to go through. And what's interesting about this use of anycast is that it's not that the origin server has an Anycast address. We've got a private tunnel from each of the Anycast centers to the origin server. And so we do this triangular forwarding. The Anycast server responds directly to the client. What this means is that even if the underlying routing changes and the client's packets go through a different packet scrubbing center, a TCP connection would not be disrupted because the Anycast servers, besides scrubbing, are just doing forwarding. They're not terminating connections. So I'm gonna, Ken, I'm looking at the clock here. I'm very close to finishing. How many minutes do I have to speak?
Well, if we're going to have questions, maybe 4.
Okay, that sounds fine. So in 1 minute, I'm going to tell you about a failed attempt to do something new. We tried to move the application server from the 3-tiered architecture onto our edge servers. So we were helping with just web servers. We moved the application servers there. We put a huge amount of effort into supporting IBM WebSphere Java servlets on our edge servers. So you could run your own edge Java applications. And it flopped. And the reason it flopped is because the programmers in these systems expected the application server to be on the same LAN as the database. And their programs made serial calls to the database. But now we introduced this huge wide area latency. That was one problem. The other was, you know, any application that could make use of a lot of application servers, like scaling up, it just moved the bottleneck to the backend database. And we didn't have a solution for that, at least at the time. And so this was a neat idea that didn't go anywhere. And it's been, as far as I know, Edge Java is not even available. Another thing we tried to do was add a supplemental peer-to-peer content delivery service. We bought a company called Red Swoosh, which was Travis Kalanick's startup before Uber. And in fact, he hatched the idea for Uber in an Akamai office during the year when he was supposed to be, I didn't say supposed to be, when he was helping Akamai integrate Red Swoosh's technology. And so the idea here was to try to reduce the cost for content providers to deliver large files. We're not going to charge them for bandwidth because the bandwidth is being provided by peers. And so we had this BitTorrent-like architecture with a lot of peers and a little bit more heavy-handed centralized control than BitTorrent. So we have these control servers that kept track of which peers had which content, and they would coordinate the peers and tell the peers, okay, here's who you should ask for content. In addition to that, if content couldn't be found in the peer-to-peer network, the CDN always acted as a backstop and could provide the content. And this worked in the sense that it was widely adopted. I think even today there are tens of millions of installations. The clients are all over the world, much better diversity than Akamai's server clusters. For clients who turn this on, 80% of the bytes end up getting, I meant to say customers who turn this on, 80% of the bytes get delivered by the peers as opposed to the CDN itself. And the performance wasn't so bad. Roughly speaking, it was twice as slow as if you went to the CDN. But it didn't catch on, and the two reasons for that are, well, number one, it didn't work very well for video, and that's most of the bytes anyway. I'm not saying you couldn't have made it work for video, but this offering didn't. And the second thing is that while it was fine for software downloads that happened in the background, it turns out that a lot of time there's a human sitting at the desk waiting for even a really big software download to complete, and they hate it if it takes too long, and the content providers decided they would just pay for this factor of 2 improvement in speed. So let me finish by saying a few things about implications for ICN. Now, I'm not really an ICN expert, but one thing I know for any system to be successful, to make it in the field, is that the incentives and costs have to be aligned. Now, we've talked a little bit about I think the beauty of the ICN service model. The service model, it makes a lot of sense that it should match what the people want to use the network for. And the IP model doesn't directly match, although as you can tell, a lot can be built on it. But regardless, the incentives and the costs have to be aligned. The benefits, the people who receive the benefits have to pay for the costs. And I'm going to talk more about performance benefits, in particular performance benefits from caching, not the convenience benefits or the security benefits. That's out of my scope of what I can say. But for the benefits from caching, the performance benefits come down to reducing latency, which is really valuable to content providers and to some extent to the end users, but it's hard to get them to pay for stuff. And then reducing network load, which is valuable to the ISPs. There's a fundamental question about, well, if you're going to use caching to do this, can you get away with caching just at the edge, or do you also need to cache at the core? And depending on where you do the caching, you have to figure out who's going to pay for it. This recent trend towards delivering everything over HTTPS makes traffic opaque. That's a problem, right? Routers can't see what's going through them anymore. That makes caching difficult. I think it's really ugly that Akamai is terminating TLS connections with private keys that belong to content providers, but I think having routers do that would just be out of the question. On the other hand, we shouldn't say that, you know, this stuff is written in stone. New protocols can be implemented and can be adopted. Quick is a recent example. So I think it's totally fine to design new networks, new network protocols to support new functionality, but we may need that. And with that, I'll stop. Ken, you've been a great audience, and I'm sorry if I went over a little, but I'd be really happy to answer one or two questions.
Okay, thanks, Bruce. That was terrific. We do have a couple questions from the Slack channel. So one from Karen Solins. I thought Akamai had actually come to the conclusion that using DNS server as a proxy for where the client actually is was not the best way to go. And she thought there was a paper from a few years ago about an alternative, and she wondered how that related to your 30,000 concentration points.
Yeah, hi Karen, I'm nearby. I don't know that I would say that Akamai just determined it wasn't the right way to go. This thing was forced on us by Google starting with, you know, Google DNS and by OpenDNS. And you're right, there is a paper in SIGCOMM by Marcelo Torres and Ramesh Sitaraman and others, and I'm sorry if I forgot their names, that talks about what Akamai did to support the new DNS extensions that provide the client prefix. I think that's actually great. I mean, it's better just to directly know where the client is. It's not very prevalent yet. That is, the percentage of DNS requests that we get that come with that information isn't so high yet. I think long-term, that would be a good transition. But for the moment, we can't change what's being done for the vast majority of clients that are just using traditional DNS. I hope that's what you were asking about.
Okay, and then another question, this one's from Dirk Kutcher. Do you think the growing use of over-the-top live video will require technical changes to the Akamai live streaming system, and would that affect the economics, perhaps?
Yeah, so that's a good question. It's possible. So, and over the top, we're talking about sort of video, pre-recorded video delivery to the home or live video, but not so much video conferencing, I think, because Akamai is not really in that business. There's been a lot of thought and discussion with ISPs about whether we could build in some Akamai functionality into the set-top, the TV box that now, you know, delivers TV over IP. I don't know where that's going to go. It's taken much longer to develop than I would have expected it to. And I'm sorry, Dirk, thanks for the question, but you could imagine Akamai having a presence in smaller and smaller devices, but at the moment, that's not what's happening. There are these huge clunky servers still, and that's sort of the only hardware platform.